All right. um, Welcome to lecture 3 for IGM455. We're going to start talking about the optimization of programs a bit in this lecture, and how we can accomplish that, as well as some of, we're going to start to kind of talk a little bit about more how a computer deals with certain kinds of code, functions, and what's the underlying architecture very quickly into the next set of lectures. So optimizing loops is a really good place to sort of start, 'cause it starts to get us into the architecture. It makes us start to think about how does this software work, how does the computer underlying us sort of, fit into, the humble for loop, for example, that we've probably written, hundreds of times at this point. Or thousands or millions, I don't know, probably way more than 100. But yeah, so let's kind of get into it. Now let's go. So let's take a very simple example. This is something you've probably done many times, and this is to initialize a 2D array. We talked a little bit about this in the previous lecture with regards to two different ways to do this, one of which is significantly more performant than the other. But let's think about it kind of from another direction. So let's ask a few questions. First off, does the initialization vary? As in, if we do it in one way or another, is it different performance, different benefits? What are the pros and cons? Also, why do we need to initialize the data, right? If, say, we have a 2D array full of garbage, does that impact our application? Obviously, there are many cases I can think of where it would. For example, if you have a screen buffer and the data in that buffer then immediately gets presented to the screen as soon as you turn your computer on, well, if you have garbage data, you're going to see a bunch of noise, which is not necessarily the intention and what we want. But in many other cases, say we're building a database and we know that we have, say it's a class, right? A 2D class of, like, imagine desks, right? And we want to populate that, as people come in, and we can have a bit that represents if a person exists in that location or not, separate to our array, which that array would be a 2D array representation of names, for example, of the students that are in that class. Well, we would just have to initialize that bit array or even that bit mask, and then use that as a lookup into our other array, which we don't have to initialize, because we're never going to access a point in that array unless we know that there's a student there per that external data structure. And so you can kind of see how in that case, say boot up time was critical, right? Because all the students are hitting us all at the same time. Then you might be like, what? When would that? That's not a realistic example, but actually that kind of analogy works quite well for a lot of networking type of applications. Say we have a buffer of data we're going to receive, and we know we have to spin it up and receive that data immediately when we have that request. We probably don't want to initialize that buffer. We just want to allocate the buffer. And actually, you'll find this paradigm also exists in in graphics programming, where we want to allocate. If you've used OpenGL, right, you allocated the data, but you didn't initialize it. And that's because, well, what's the point of initializing the data before you use it in this case? Now, you can use that data before it's initialized or populated. Well, you're going to get garbage, but at least it's down to you as the programmer to be control of it. So actually, that particular subject is a big one, that particular question. The other day, like, what kind of data is it? We already kind of touched on this in the last example, right? Is it a name or is it a number? That's going to really fundamentally change how we initialize this data, right? Is it a array of pointers to memory, or is it something else? What are we initializing it to? Is it a 0? Is it a number? Is it a data? Or are we loading data from some other place? Where in the hardware are we running this, right? Is this in the stack? Is this in the heap? Is this off of a cache? Is this off of memory, right? There's a lot of different places where, we can very easily think to ourselves, okay, a 2D array of like 5 by 5, that's going to exist in, potentially even in the stack, right? But what if we're talking about, gigabytes of data, where data has to be loaded into memory because not all of it can fit, and you sort of have to do this, thing. And then also, what's the compiler? The compiler has a lot to do with the code that ultimately, I wouldn't want to call it code, but the instructions that line up and actually produce this outcome. And you can imagine that the compiler actually, in particular with these kind of lower level operations, will have a huge impact, right? Because how efficiently it can understand what you're trying to do will reflect directly into how efficient this code is. And this is the kind of stuff where, look, like when I have to copy a buffer, even still today, I get a bit of an anxiety because I'm like, am I doing this in the most efficient way? Right? It's one of those weird issues that like never goes away. You can never like be confident because the compiler and all these subsystems, it's almost funny, this like stupid little thing that we do multiple times in any program is actually one of the hardest things for the computer to do efficiently, because it actually is loading the computer, right? If you think about a computer, which we'll talk about in the next set of lectures with the architecture, is simply a machine that loads out of memory and then stores it, right? The initialization of a memory location or an array is literally that, and do it as fast as possible. So you're basically asking your computer to go sprint as fast as it possibly can for a moment, and actually taxes the computer architecture quite heavily. The other examples of these kinds of things is like floating point operations and so on, but you'll find that the limitation in most computer systems has to do with the bandwidth of the system, be it between memory, be it between the architecture, like not memory, but the bus and the architecture, like between the different components, right? Like in pertinent to graphics programming, obviously is the bus width between the CPU being not really the best example here, but like the CPU side and the GPU side, right? And in fact, there are many hardware components in a computer system that aim to aid with that. For example, if you're familiar with OpenGL, is what's called a pixel buffer object. And what this exposes is actually what's called a direct memory access bus. So instead of going through the CPU, there's a particular bus in a computer that allows you to read directly from memory into a particular peripheral. And so what you're doing here is instead of the CPU acting as proctor of that memory in memory, passing it to the GPU, instead the GPU is directly connected to that location in memory by way of DMA. And that way you can update that memory and the GPU will automatically get that update without the CPU being in the loop, which you can imagine is critical for like video streaming. And by video streaming, I mean streaming the video to the GPU. So say you have a texture that you want to be updating on a regular cadence. Every language, every API will have kind of an exposure, like an ability to access those kinds of architectural components, which we will probably talk about in the rest of this course. And then finally, I mentioned this earlier, like how efficient does this have to be, right? Does our algorithm have to initialize it on time, or can we do it sort of what's called lazy loading, right? Can we load it sort of concurrently? And we'll talk about some of those subjects in this lecture. So let's go into it. Let's think about, let's think about the sort of for loop. And we brought this up in a previous lecture, right? This sort of vanilla way of doing this completely wrong, where we're doing essentially column first setting of a value. So here, remember that the J and the I are flipped, right? So the top level nesting is actually incrementing the secondary, the column versus the row, or whatever you want to call it. There's no row, column, row preference here, but essentially the second dimension of this array. And this is going to effectively skip over every row. In our case, right, if you think about contiguous memory, right, each row is basically like a linear array, and then you've got the next one. So the distance between one element of one column, I'm calling column J, I'm calling the second array as a column, but again, there's no specific ordering here, but this is just nomenclature that I'm using. So given one element of one row and the element of the next row below it, if you're going basically indexing by a column in that sense, then you are going through, you're basically adding size to that memory location, which in many cases will break your caching and the efficiency of your cache, or the efficiency of your system. And this is why it's going to be significantly, maybe at low, small sizes, it won't really make a difference because you're not hitting cache yet. But at a large enough memory size, you will start to see significant slowdowns because of what's called cache misses, which means that the memory you're trying to access is not in cache, and so the computer has to load that into cache and kind of switch things about. These days, caches are quite large, so this has to be pretty big. But if you're in the world of like gigabytes of data, this will take 20, like way longer than the alternative of IJ, due to the efficiency provided by cache coherent, the temporal efficiency provided by working on the same memory location. So yeah, this is pretty bad. This is what's called, it's going to thrash your cache, where the cache is constantly loading and unloading pages. Oop. Cool. So this is the better way, right? This is a tight loop. It's basically going memory location to memory location. This lines up with the way that we're storing the memory. And this is also kind of intuitive, right? If you're nesting the loop in this way, then it's basically you're going line by line and setting each one. But is this the best way? Well, that's complicated. So if we actually can get help from our compiler to do this. For example, let's talk a little bit about the computer in this case, before I go on and talk about how the compiler can assist us. What are some ways we could potentially do this faster, just theoretically? Right? In this case, we're setting each memory location to 0. And so what I want to point out there is that each operation, that int array ij equals 0, is actually independent regardless of the ij, meaning if we had two computers that somehow magically could access this array, and they were doing this at the same time, right, assuming that there's no memory collisions and bullshit, assuming they're both doing it, right, we would imagine that this could happen twice as fast. If we had 4 computers that could magically do this simultaneously, it would be 4 times as fast, because int array ij for one value of ij and another value for ij do not affect each other, unless they're equal. But even still, if you're kind of on top of each other and you have a race condition, you're still going to get 0. They're both trying to do the same thing. So in short, if we could somehow spread this out across multiple computers or multiple sources of work, this would actually speed things up quite substantially. So kind of keep that in your mind as we start to talk about how the compiler can potentially do this. And I won't talk too much yet about how the architecture of the CPU is going to accomplish that. We'll talk about that in later lectures. But you can kind of already hear where I'm going. If you're familiar with modern computers having multiple cores, and they're all sharing the same cache and memory, you can kind of hear already, well, that's actually a really straightforward way to do it. Now, modern computer systems are obviously doing a lot with their CPU, a lot of other things going on, so we're going to just ignore that for now. We're going to ignore the operating system and other programs running in our vicinity, assuming that our CPU this is all we're doing right here. So let's talk a little bit about intrinsics and what the compiler can do. These are functions that are sort of optimized specifically for the hardware that we're running on. So the compiler is aware, obviously, of what the underlying hardware architecture that we have. So are we on ARM? Are we on x86? Are we on AMD 64? What is the specific architecture? And when you're on a particular architecture, you are guaranteed certain capabilities and certain sort of architectural components and mechanisms. And so you can write specific kinds of functions that leverage those mechanisms. And in many cases, this actually goes quite deep, right? Where you have a particular CPU implemented on a particular architecture, but made by a particular vendor, say Intel, and they expose what's called extensions, right? And so, companies like Microsoft, for example, have very close relationships with Intel and AMD, because as Intel starts to bring in these extensions and more complicated, things, like for example, there is a class of instructions on a CPU called what's called multiple single instruction, multiple data, or SIMD. And if you're familiar with this, it's basically the ability to do exactly what we're talking about, which is you have one instruction that somehow applies to multiple locations and data. And we'll talk about that more in this class. But the compiler can notice this behavior, this pattern that we're trying to do, which is set all of this stuff simultaneously and utilize those intrinsic functions. So in Visual Studio, to enable intrinsic functions, you use the option OI, or you can do this in the optimization tab for the project. So most, when you're using a particular compiler, be it Visual Studio or GCC or whatever, just keep in mind you may have to explicitly turn on these kinds of things. And if you are interested in more information about this, here's a link to the compiler intrinsic functions that Microsoft provides. But we won't get too deeply into this. So, although we will talk about memset. So you may already be familiar with memset. Memset is not explicitly an intrinsic function, but underlying its logic, obviously compilers do a lot of funky stuff like memset, memcopy, these malloc free, whatever. These are functions that are operating at this level and are sort of the bottleneck, like not a bottleneck as in they slow things down, but they are the sort of gateway to a lot of the underlying optimizations that are provided by compilers and architectures. So let's talk a little bit about memset. What does it do? Well, it just takes a location in memory and a size, right? So you're saying, okay, starting at this memory location and ending at this memory location, I want to set all of that data to a particular value. More often than not, you will see memset 0, and you can actually, there are variants of malloc, for example, like calloc, that kind of combine memset and whatever, and there's like a million, I can't think of them off the top of my head, but when you go and you look at memset, memcopy, next to it, you'll see a lot of variants of it, so in one line of code, you can allocate the memory and then set it to a value. But for the most part, underneath, it all kind of works the same. So there's no optimization, you're just saving lines of code. So in my experience, personally, and this is my opinion, I like to be explicit about what I do. So I like to allocate and then set the memory. In fact, my style of programming tends to allocate in the constructor and do nothing but that, right? This is in C++, and then separately initialize, and the initialization would then give you a lot of this stuff. So the two, because allocation can fail and initialization can fail, but in very different ways. And so you need to, the way I like to develop large systems is to kind of separate the two. So this is just one section of that. So let's think about, what's faster, right? How much quicker is this than doing the for loop explicitly, right? So with that, I was gonna do this in Vim, but because we kind of want to have the profiler set up, let me do it in C++, in Visual Studio. So give me a moment, I'm going to pause, I'm going to set that up locally. Okay, sorry about that. Cool, so I just set up a little thingy here, and hopefully you guys can see it. I'll try to zoom in. I will probably post this as a kind of a whatever repo if anybody's interested as we go, but for the most part, this is all going to be just kind of garbage, sketchpad type of code. So don't feel like you're missing out if you don't follow this or whatever. Cool. So let's do a quick test, right? Let's create this function array3. And I apologize, I'm not going to be using like the most clean code in the world here. I'm just going to be kind of doing this quickly. So let's call this memset set array memset, right? And then we'll take in a int array and some kind of size that we will then use, and then we can call memset on this, which is going to be the pint array. We're going to pass in a value, 0, and then we're going to use size of int. Although if we want to get fancy, we can go template class t, right? Let's do that, because I am a jerk. Cool, so there. And we're going to do this. So now we can set array memset blah blah blah. If you're not familiar with a template, that's just a generic, so it allows us to call this function for whatever we want. So let's start off, and we're going to create a new integer array, and p int array, oops, is equal to new int, right, we can't just define a number. We're going to call it size by size, right? Or if we want, same thing as this. And then we're going to, I'm going to assume it's not null. Well, we'll do this. If p in array is not equal to null pointer, then we're going to set array memset, and right, to the p int array, and in this case, let's do this, size t pan array underscore n is going to be equal to size times size, and size of int. Cool. So that's going to be our pint array. This is just my sort of pseudo code convention if you're curious about what this underscore n and what the p means. The p means pointer. The underscore n is sort of my way of indicating that this is the size of a array, or a size of something, underscore n. I do a lot of these weird things like that, like underscore n is like the size, underscore I is like a counter or cursor, sometimes you see. Anyways, just fun things. So let's see if this actually runs. It failed. Int to int. Cannot convert. Alright, I'm just... memset, identifier not found. Why? I always forget what to include here. One moment. Right, I always forget. For whatever reason, to get memset, you have to include string, because that makes sense. But yeah, great. So now all succeeded, and if we run hello world, we're now calling memset, and we just blew up the code. That is because the pint array is very large number. Let's see why that is. So we might already be doing something stupid. That's mostly likely because the pint array here is a garbage number, which is very large. In this case, looks like how many zeros is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Too big. Let's make it smaller. Let's start with 1,000 by 1,000. I think that makes more sense. Great. So now we'll be at 4 million. So 4 megabytes, not really, but okay. And now when we call this exception thrown, still exception thrown. Why? 1 second. Let me figure this out. Sorry, I'm just an idiot. I'm doubling up the size here. So if this is the size, then that's not then I don't need to do size of t here. I was kind of outsmarting myself. Okay, so, okay, cool. And now we run it, and great. And now our int array is a whole bunch of zeros. We'll assume that that's the case. We can actually test here in the in the watch. So you can actually do things like pint array plus 20 in the debugger here, if you're ever wondering. And that'll just increment. You can actually do quite complicated conditionals and casting and all that stuff down there if you're curious. And so yeah, you can see everywhere is 0. Now, maybe we want to be able to measure the time. So I'm actually going to pause and write out that code really quickly because I always have to look it up. One moment. Okay, cool. So I haven't compiled this or anything, but basically I've added chrono, and what we've done here now is we basically created, you're reading the time now, and then you're reading the time when complete, meaning just basically the time, and then what we're doing here is we'll take time now minus, time complete minus time now, and we're using the millisecond for chrono, which something went wrong as usual. Chrono milliseconds, and great. So to then, let's simply print the time set array memset for, great, elements in a 2D array took milliseconds. And the number of array elements we're doing here is a p int array n, and the ms duration value. Cool, and let's see what we get. So, let me get rid of this hello world, or at least add a new line so we're not going crazy. Cool, so set array for what looks like 1,000,000 elements in a 2D array took 0 milliseconds. That doesn't seem right, or it might be, because it's actually that fast. So perhaps we want to get down into the nanoseconds and see if we can get anything. We're getting nothing here. Time complete, milliseconds. We're in debug mode as well, so let's see if we add a size here, will we start to actually take up any time? Still 0 and we're 0, so this is suggesting that maybe our code is not working because that clearly took some time. One moment. Let me pause and kind of debug this. Okay, sorry about that. I am not thinking. So let's go to milliseconds again. The issue was this was a float, and that should not have been a float because ms duration is not is a long. Okay, so anyways, let me go back down to 1,000. So we'll have a 1,000,000 sized array, and what we'll do here is let me pause on that. And now what we'll see is we're going to run this, and we're here. ms duration is going to be 0 still, because I guess it's still too short of a time. So let's go down to microseconds. And you can see just how fast the computer is here. So okay, we're to set 1,000,000 array elements in using memset is taking us about 85 microseconds. Let's change this quickly to reflect the correct values that we're doing. Let's add a little bit. So now we're going to be doing 100 million. So to set memset to 0, a 2D array, is taking us 19,000. You can't read it; it's quite small. Here, I'll make it bigger. 19,000 microseconds. Great. So now let's create a similar function. So set array for loop, and we'll do a 2D for loop, right? And here we're going to take in a size. versus a, in fact, let's do this. Let's make sure that everything is correct here. Set 2D array. Right. And instead of this, we're going to pass in size. And we don't need this any longer. And just update this. Set 2D array for 2. Great. So now we're just going to run it. So for a 10,000 by 10,000 2D array, it took us 26,000 microseconds. You'll notice actually that actually made a relative difference, right? Before we were at 19,000, so that actually added 3,000 microseconds, just the size times size. So you can kind of see already, right, like how crazy, right? Like if I just go back really quickly to doing it this way, you'll notice that a different thing. So now it's actually 28,000, 23. So clearly, size t pint array, this approach actually sped things up quite substantially for us. And if you really want to get an intuition of why that is, oops, doesn't look like it's sped up. Now we're back up. So maybe that is not the case, because we're still at 23. So I don't know. The intuition, by the way, to me, actually this should be fastest. If we simply pass in size by size here, that in theory should actually be the fastest that we can get. And the intuition for that, by the way, is that this is not happening, this calculation is not happening real time. As in runtime, this is happening at the compiler level. So when we compile our code, it looks at this and it replaces this particular statement with the final number. And then it compiles the code. So the preprocessor actually comes in and does all of this for you. And that's the reason this is going to be faster. In fact, if we put in, say, 4, which is the size of t here, we may be able to even get faster performance. Not really, it looks like, but whatever. So let's stick to, let's go back to this approach so we can create some relatively consistent functions. Cool. Okay, so now we have this. Let's build our 2D array for loop. So we're going to have a for int I equals 0, I is less than size I plus plus, right? For int j equals 0, j is less than size j plus plus, and then we're going to take our pint array I j equals 0. So now let's repeat, just basically cut and paste this code. So this is our memset, and this is going to be our for loop correct. We'll mess around with the alternative in a minute. So we're going to do here is set 2D array for loop, right? And for loop. And keep in mind, right, there's going to be some delay between time now and actually calling the function, but let's just assume not, right? It's all good. And so let's see here what happens when we run this. And no, failure. I wrote bad code. That makes sense, because I always write bad code. The reason is we don't need to redefine things. Subscripts require array or pointer type. Great. Friends don't let friends use raw pointers, but hold on. I'll be right back. Okay, I clearly am not going to get away with this unless I do this, which nobody wants. So I'm going to have to refactor this code a little bit. This should compile, however, which kind of C-ish code that, all right, I'm not having a good day. Let me fix this so that it actually works, because I have to make this a double pointer for us to be able to double index into it. Okay, so yay, because I insisted on using a dynamic 2D array, I had to include this code here. It's a bit verbose, but basically creating the int array to null, initializing it as an array of int pointers, and then going through each one and then initializing that. There are better ways to do this, like with malloc, but that's okay. We're not going to talk about that right now. And now I can index like using the way that I want to demonstrate for this example. So cool. Let's see if this actually compiles. Looks like it. And let's run it. And so now, oh cool. That's what I've always wanted. Another mem issue. What is the issue today? And that is that I need to dereference this guy, I believe. No. One moment. Okay, the heap got in my way. In short, because I was doing the dynamic allocation, memset doesn't work because the memory is not contiguous. Okay, cool. We all know how dumb I am now. Great. So now I'm using malloc because that's the good way to maintain one contiguous allocation of memory. And now this should work. Or not. I'm having a great day here. Pause. Okay, I'm back after what was way too long. Let me explain what was at the core of this, because I think this exemplifies a particularly tricky bit. So, where memset operates on a contiguous chunk of memory, the problem lies in that actually is treated as a 1D array. So memset cannot actually operate on a dynamic 2D array. So when I was actually trying this out, I was trying to do things like, you know, p2d array is equal to int size. And you'll actually notice, because I'm in debug mode, this won't optimize, you know, oh sorry, not like this, just like a static array. Now the problem with this, you'll find out very quickly. So when I run this code, I will get an exception on main. What the fuck, right? Well, the reason is because size is 10,000 times 10,000. That's 100 million. That's really big, and I just blew up my stack. When you create static, you know, variables like this, basically you only have so much space to work with. Your stack isn't that big, and so you hardly ever run into that on you know, PCs and desktops. You run into it all the time with embedded. You always have to kind of map out your stack and how much space you have and so on. But yeah, so static 2D wasn't really possible. Now, the nice thing about a static 2D array is that it is a contiguous chunk of memory, right? The stack is going to start at a certain point and go down. We'll talk about stacks in the next lecture even more. But yeah, it's basically impossible to have a stack of effectively 400 million bytes. Your program will get really angry at you as you did. So I had to kind of split this up into two pieces. The flat array here, in fact, I'll just make this sort of correct in that it's a double array, but we're going to treat it like, so a double array, a double pointer allows us to, you know, allocate this properly. And if we were to index into this with, you know, our indices, we would be able to access that the way we want. And then separately, here is a 2D array that's dynamically allocated, where you can see you create one array of integer pointers and then another array of a list of integers. And so you can kind of see the two of these are being, one is, they're two different pathways here. I think if I hacked on this enough, I'd be able to unify them, but for now, let's just leave it alone. So let's run this, and we can actually see the difference in time, where you can see that the memset, where we set the 2D array with memset, it took 25,000 microseconds. However, when we went for the other one, it actually took significantly more than that. What looks like 154,000 microseconds, which is, you know, roughly 6 times longer, which is quite a jump, right? Now let's try that thing we did in class, right? What happens if we switch the indices? You can actually see, in this case, not only did it go up, it went up to 886,000 microseconds. So just that, like, if we do this kind of, if we duplicate this, set array for loop wrong, whatever, and we duplicated this code here, and we used instead a wrong, and we run this, you'll notice that, right, for the, sorry, this is quite annoying. We want to get some new lines in there. You can see for the memset, it was 31,000. For the 2D with the indices with the for loop, it's 151,000. And then in the case of when we flip the indices, it's 913,000. Quite a jump. And let's like add one order of magnitude to the size, so everything's going to take kind of a while now. So, you know, you can kind of see how one order of magnitude has now, you know, made our program actually take quite a while, even for the memset. Most of this is probably an allocation, because this is about a gigabyte of, yeah, we might actually kind of be taping out. I'm looking at my process profiler here, and I'm at 41 gigabytes of process memory. So we kind of have choked out the program. Let's maybe just double, not an order of magnitude, but double. And we can see that the process memory right now is up at 3 gigabytes. And you can see kind of what I was trying to demonstrate, which is the memset, which only took 121 microseconds, was still reasonable, right? That's about 121 milliseconds, still within reasonable bounds. I mean, it's a lot of data that we're dealing with, right? Then the 2D array actually took 600 milliseconds, 600 milliseconds practically. And then the 20,000 by 20,000 elements, when we flipped the array indices, we're actually up at 4.5 seconds, which is quite substantial. So you can kind of see how just a small difference, these are all doing effectively the same function, and they do produce a very different result. So let's go back to our lecture. Thank you for, so memset, you can see it does really well, but it doesn't do well for other kinds of data like floats and doubles. It doesn't solve for all the initializations, right? We can't, as we talked about in the last lecture, floating point representation for 0 is the same, but if you say wanted to set a bunch of floating point numbers to 3.7, it would be relatively difficult to do that. I mean, there is a way to do that with memset, but you kind of have to be clever about it. You have to sort of back into like all this stuff. So it's not a trivial thing to do, although it's possible. So let's talk a little bit about the loops and the hidden branching of loops and what we can do to kind of improve things. So say we have a conditional, such as if the player is running, right? This is what's called a branch. If it's true, then we do the stuff in that section, and if not, then we do the stuff in the second section. You may notice some of my humor in here if you click on that link. Ultimately, every loop has to make a decision every single loop, right? So we're going through this loop, and we eventually want to return the value 42, right? And we're always kind of checking, are we less than 42, or the size, or whatever. So we're always doing this branch check, branch on conditional, or a jump on conditional. So let's take a look quickly at what a for loop actually looks like in assembly. And I've annotated this a little bit more than what was before, so we can kind of see a lot of these are particular registers that you may not be familiar with. And don't worry if you don't really know all this stuff. The need to implement stuff in x86 assembly is relatively minor. I've never had to do it myself and had to look up most of this as well. So to start, right, we can see here what's happening is move dword pointer $1 EBP 0. What's going on there is we're effectively setting the memory location of I. So whatever the value, like wherever I is in this memory location of $1 bracket EBP. This is a way to sort of index into memory. And what we're doing is we're moving the value 0 to that location, which is the memory location of the variable of the variable I. So that's all we're doing here, is just saying int I equals 0. That's what this is accomplishing. Now we're jumping to ln4 at main, which actually goes down here. And this is kind of a surprise, right? Like, why do we do that? Well, say we were doing for int I equals 0, I is less than 0, or less than equal to 0, then I is already matched the conditional, so we don't do the for loop. Why would we ever do this? We wouldn't, but to be a kind of concise language, we have to sort of cover that base. Say I calls a function that returns a value, and in some cases that value means that you don't want to run the for loop, for example. This jump to ln4 versus ln2, which would mean the actual body of the for loop, allows us to do stuff like that. So verbosity to allow us to not have to worry about, edge cases in the language. Cool. So now we're here, and now what we're doing is we're comparing I to 6000. And the way we do that is, you can see we use this assembly call called compare, CMP. And what it's doing is it's looking at the value 6000 and the value that's found in the memory location of I. And keep in mind, and this goes into kind of the computer architecture a bit, all we're doing is we're setting operands for a what is then a ALU, or arithmetic logic unit, function of some kind. So your ALU will do add and subtract, multiply, divide, but also compare. That's actually one of the most important functions of an ALU, to look at two different values and say output, is it greater than, lesser than, or equal? That's actually something that we do a lot, and so the ALU does that, is sort of as an explicit function. So here you can see this called JGE, jump if greater than, or greater than equal to. Actually, I mislabeled it. So what we're doing now is we're taking a look at that output of the comparator, and if it's greater than or equal to, then we jump to ln3, which means that in this case we basically were greater than the value of 6000, and that means that or equal to it, right? You can kind of see the inverse here. We're checking if I is less than size. Well, the inverse of that is I greater than or equal to 6000? And if it is, then we exit the loop. If not, then we move on into here. And what this is doing is it's adding sum, 1 to sum, really. I mean, you can go through this if you'd like. EDX is actually a data register. You'll notice this pattern where we load a value from memory, then we add, like we operate on that value that we've loaded. We're not operating on memory directly, but we're operating on the data in the data register, which is the EDX here. And then once we've produced that output, then we load it back into memory. And the reason is we can't really apply ALU operations directly to memory. We kind of have to bring them into a local register, because in the ALU is not connected to memory directly, right? And the memory, and keep in mind, there's all these fun, like kind of architectures on the CPU to determine where that memory is. That memory could be on the hard drive, and if that's the case, it kind of has to kick off an I/O load and all this crap. So there's a lot of stuff going on kind of in the background of the CPU and the system that allows for this to happen. Now we've added one to sum, and we're going to go to ln2 back to here. And what this does is kind of very similar to what's going on here in the sum++ area. And we're just adding 1 to I, and then we're comparing it. And so this just happens over and over and over again, and then you eventually bounce out to main. So branches are pretty expensive, all right? They do a number of things. They're changing the stack pointer. They're changing the program counter. They may involve changing the stack pointer. There's a lot of stuff that can happen, but branches are not particularly predictable. And when you're dealing with hardware, the hardware does very often, the CPU does have what's called a branch predictor. There are a number of different algorithms, and in some cases actually a CPU will, when approaching a jump, the CPU will sort of go down both pathways, not knowing why, what will ultimately happen. Because of sort of what's called superscalar processors, which are able to take multiple instructions and sort of split them across multiple pipelines. So a superscalar processor is kind of like having one CPU pipeline, many CPU pipelines in one computer. And so you can imagine, well, if we can do multiple things in parallel, right? If we have a particular line of, set of operations that sort of depend on one another, and then you have a branch and it can go in either direction. The idea is that you take both, and then you kind of find out what led to that, and then you basically say, okay, we're going to stick with this, and we're going to nullify what happened on the other branch. But anyways, this is actually like a whole computer architecture discussion, and for the most part, what you need to know is that sometimes the CPU will take both branches. In fact, recently there was a big computer CPU architecture bug, like a vulnerability as a result of this, that branch prediction led to what's called Spectre. And what the vulnerability was, it was possible to actually leverage one of those predicted paths if done in a correct way. I don't know the details personally, but what was possible to do is if your branch predictor took a path and then that was not the path that it ultimately took, like imagine comparing a password to something, you were able actually to go to the path where the password was correct, even though if the password was wrong, like you were able to sort of flip it. That's a very big simplification of what's actually going on there, but yeah, branch prediction is something that the CPU does a lot, as much as possible, because branches are expensive, or taking the wrong branch is in particular expensive. And when you have a lot of, in CPU architecture, the name of the game is to maintain maximal utilization of your hardware. Meaning you have all these pipelines and they work in stages, and you kind of want to have them filled up as much as possible. So it's better to do two things, one of which will get canceled if you can do that, and then speed up overall, because you're not waiting, right? You're like, this is, yeah, we'll talk about this more in the next lecture, actually. So that's actually one of the reasons that loop unrolling exists, because the branch is quite expensive. So if we unroll a loop, meaning we kind of treat the loop as if it happens, like as a sequential piece of code, we can actually really help out the CPU, both in terms of avoiding jump operations, which are relatively expensive, but also by way of allowing a superscalar processor to better allocate its resources. So we talked about this example here, right, where you're effectively setting this value, one after the other, but those sets are effectively independent of one another, right? I can set multiple locations in memory and it won't really affect me, because those operations don't affect each other. And so I just mentioned the superscalar processor will have multiple pipelines and multiple resources. So you can imagine if you could sort of take this line and then duplicate it to the number of superscalar, or to the amount of resources that we have, and then the CPU can see that, and say, hey, we can actually dispatch this to the individual resources that we have and have those happen in parallel. And now you've sped up this entire loop by a significant amount. And so one of the ways that we can actually sort of tell the CPU that that's what we want to do is by rolling out the loop. And so what is this unrolling? What does that mean? So here's a very simple example of rolling out a loop. We basically, instead of incrementing in the for loop by 1, we're doing it by 2, right? So instead of setting each one, we're actually setting 2 at a time. So let's see how that functions here. So let's take a look at our set2d array loop, and let's just copy that and make another one, set2d array loop 2. And what we're going to do here is instead of plus, we're going to do plus equal to 2. And here, and we're going to do plus equal to 2. Actually, I'll keep the plus plus on the I because this is, right, so we're going to do j and j plus 1. And we have to make sure that j, well, the divide by 2. So we might, this is not particularly robust code. Keep in mind, I'm not really taking care of odd numbers of things or whatever. But oops, keep on hitting the wrong key here. Butterfingers. Okay, so if I go 2D int array, and I just do set array 2, and let's see if this particular function will be faster. Let me stop this because it was way too long last time. Okay, we're going to do it for 10,000 elements. And let's see what we got. And so set array memset, 23,000 microseconds. Set array for loop 2 took 200. So we actually kind of went down from 160. Or we went actually down substantially, which is a bit of a bummer. So not always is this true. Perhaps we can do this in release mode. Oh, I don't have a release configuration, which is always nice, because I used CMake, but whatever. Let's see if we can kind of hack it by doing plus equal to 4. And let's see at what point do we actually improve our performance. And you can see actually it didn't take too much. Right now, 20,000 microseconds for normal memset. And for the for loop 2, we're already down to 103 by rolling out the loop into a set of 4 versus 165. So let's do this even more, right? Let's see at what point do we kind of tap out. Let's do 10. And keep in mind, I'm really not paying attention to. Oops, I just did something pretty bad. Here we go. Great. So let's see what happens. And you can actually see it scales up pretty well. So when there were 27,000 microseconds, and set 2D array for loop 2 with an unrolling of 10 is getting us down to 60 microseconds. So the question is, can we get even more? Let's see if we can get to, like at what point do we start to fall down? So we're gonna do 20 at a time. And it looks like we're starting to slow down. We're now at 56,000, so we only really gained, 4 milliseconds there. And let's see. This may break, but I just want to see if we get down even more from 56,000. And yeah, it looks like 52 microseconds. So you can see it's starting to get us closer and closer and closer. And this, I think, should really be indicative of what memset is doing under the covers. Under the covers, memset is essentially doing this. It's taking advantage of all of the different parallelization paradigms, both in terms of intrinsic functions and CPU architecture hooks that we can use. So yeah, it just one of the things, and also one of the functions that's occurring here, both in terms of the CPU being able to dispatch across multiple resources internally, it also removes that branch operation, which you can see actually in this code. The branch is one of the more common things. We have move, 1, 2, 3, 4, 5 times, but the jump is the second most common with 1, 2, 3. Very common call. So yeah, this is actually a very, very powerful optimization technique, but hard to determine when to use it, because at the end of the day, what's the point? You can just use memset, right? This is actually something that's really important for non-zero initialization. So if we use kind of a combination of memcopy and unrolling, we can kind of treat each row as a memcopy. So we talked a little bit about this already, this issue that I ran into with having memset malloc or whatever with memset or multiple array dimensions, and you can kind of see that that's sort of what's happening here, and we can do that with values like temp. And so what we can do is we can create the array length and then memcopy it one element at a time. And that is a way to do memset or memcopy in that 2D array mode, especially with regards to non-zero initializations. So this is one good way to do it. Generally speaking, though, what happens in practice is when you are trying to initialize, say, a 2D or 3D or buffer of some kind, you save it as one contiguous chunk of memory, and then you really do deal with it like the malloc that I demonstrated. But then what you do is you sort of pass it through this filter of then indexing into it in a way that allows it to look like a 2D array, and that's a lot more common than the alternative for large pieces of data. So multi-core, right? How many cores does the target platform have as a minimum? And how do we use this multi-core in programs without changing how we write things? And so this is actually where you start to kind of lean on the compiler or the development platform that you're on, or the operating system, really. Because this isn't really a compiler feature as much as it is as a Microsoft Windows capability. And while different platforms provide different versions of concurrency support, these particular ones are Microsoft specific, which is why I included the links to them. And what's going on here is we have a function called parallel4 that allows us to take a particular function, and this is an anonymous function, we'll talk about in just a minute, and dispatch it to concurrent resources like multiple cores and so on, using what's called a partitioner, that is, again, a Microsoft concurrency object. And so you can kind of see these two parallel fours. What we're doing is we're taking this, we're basically setting temp I to 5 in a concurrent way. So we just sort of pass this function and we assume we're going to get back the temp 5. Temp is now initialized to 5 across the board. And then we call parallel 4 again with this other function, memcopy, which is what we did before again. And you can kind of imagine that now memcopy for each array point is being dispatched to different potential concurrence resources. And sort of like the Windows framework will just sort of take care of this for you. Let's talk a little bit about this lambda function. And so this function that you see here, where is that coming from? This bracket, ampersand, size ti, it kind of looks like a function pointer if you're familiar with those, but it's not quite. It is a function, it has code inside, it's sort of the self-encapsulated closure. And so this is what's called a lambda function in C++. And what the lambda function ultimately accomplishes is it creates this anonymous function, and this is only since C++ 11, it's a relatively recent feature of the language. Like, for example, I don't believe that C provides anonymous functions. It might through anonymous function blocks. I know Objective-C does, but I haven't really ever tried to do anonymous in C. Although there are ways to sort of accomplish it in C, because in C you can do anything as long as you're willing to code, 10 times longer than other people, which is fine. So this is the format. You've got the brackets, which allow you to capture. We'll talk about what capture means. The parameters of that. So what parameters? It's just like a normal function. What is it taking in as parameters? And then the function body, which is just code that's going to get called. And this acts actually like a functional, like an object. This is actually syntax, like just sugar around the std the standard library function functor, or function pointer object, smart thing, whatever you want to call it. And so it's very easy to use. If you're familiar with that standard library, you can look that up if you're interested in more info on it. What's really nice about it too is you can handle it like an object. So this allows you to do functional programming in C++, and was a very much welcomed feature addition to the language. And so to talk a little bit about what a closure effectively creates a sort of local scope where all variables in that scope are accessible by that function body. And then the capture, the critical thing to understand about capture is that allows you to essentially access the scope in which the lambda function was defined. So say you have a function that defines a lambda. In that function you may have scoped variables. And so it's really important, because you may make this lambda and then return it from a function, and if that lambda is accessing scoped variables in this function that the scope has now passed, you run into a lot of problems. And so the way that you do this is important. We'll talk about capture in a minute. But this is not a function pointer. Very explicitly, a function pointer is literally a pointer to a function. So in C, you can do function pointers, right? You can create that. That's not an anonymous function, right? This is sort of the big difference. And so just keep that in mind. This is an object, and it's encapsulated. It creates, and that's the way it functions. In many cases, the lambda and the function standard library object behave just like function pointers and can be interchanged, but that's more of a functional level thing, kind of, and mechanically they're not the same. So capture, you've got this bit that gives you an ability to pass state between the lambda and its external definition, the scope that defines it. So you have a couple of different options. You have equal, which basically will copy those values, the variables by value in your local scope. This is safe because even if an object passes out of scope, say it's an integer value or something, you've copied it into your lambda, and so you don't have to worry about that. But if you pass it by reference, well, now you're in trouble, because maybe you call that lambda, the lambda code runs in some other portion of your program, and those variables have long since gone out of scope and are no longer valid, and you will have an exception, which we all love. And so, yeah, obviously all values that are defined within a lambda can be accessed within the lambda. So there is sort of this, again, if you're familiar with closures, and I do recommend kind of reading up on this more if you're interested. This is a very powerful feature, particularly useful for event handling and stuff like that. There are other forms. You can pass a reference of a particular variable or a particular variable value. The equal for var doesn't really work, so don't do this. You'll just get an error. And you can also pass this, which is a pointer to the current object's member variables, which again makes sure that this is valid, because if you do that, then explosion. So just kind of a final note on parallel for, and I included a link to this earlier, but to kind of go through this and to understand how this works, right? You start with a starting value for parallel for. This is the variable that will be passed in as a parameter. So the start and the end values. And then you have the function body, and this is provided by the lambda, which has a particular format. And then you get that scope when it runs, and it's basically just like an iterative function. So you can do whatever you want, and it will run from start to end in terms of the values. It'll pass in this variable, these numbers, just like a for loop with an integer, conditional. But in this case, it's not a conditional. It's just this is the beginning and end range. And then finally, the body of this function will be chunked across cores and threads based on your underlying concurrent resources given by the partitioner type scheme, which in this case we provided the static partitioner. Again, this is a Microsoft provided object, and this is also a Microsoft provided capability in the concurrency library that they provide per Visual Studio and Microsoft development in general. And so yeah, it's sort of like a high level explanation of the fact that it takes this function that you've defined in an anonymous function and sort of spreads it across your concurrent resources as available, much like your operating system is already doing for processes and threads and so on, but now is doing it at the level of the function that you've defined in the Lambda. So this is particularly useful for the processing, loading, saving of large amounts of data that are, say, performance critical, right? Say you're like doing some machine learning thing and your entire program is going to run over the span of 2 weeks. Like, why lose sleep over loading all your data from disk? Because it happens one time, and sure, it takes 30 seconds, but who gives a shit, right? However, if you were updating, say, a frame buffer that's being updated 10 times a second, and you have the opportunity to spread it across multiple resources, then absolutely do that if it speeds up your real-time application. A lot of this stuff is always a trade-off between effort and development time and return on effort and development time. So oftentimes engineers, and this is just more of a personal perspective, a lot of times we as engineers will focus on a particular component of our system. We try to make it more efficient, better, whatever, but it happens one time. Right? Like a really good example is the arguments processing that's done in the command line or something, or loading data from disk or whatever, where we try to be super fancy, create all these complicated things, but it gets used one time. It doesn't actually impact any of the real objectives of the application that we're building. And so I really kind of, want you guys to all think very critically about when to do something like this versus when to just do it quickly and dirty and move on to what's actually important. But it's very important to understand when that is and those trade-offs, and that's kind of why we're discussing it. Cool, that's the end of this lecture, and there's going to be a follow-up on function pointers in just a moment. See you then.